Hello and welcome in a new video. We will continue with the tutorial of chapter 1, kinematics. We will solve now exercise 24. A point M moves along a circle of radius r equal 2 meters whose angular motion equation with respect to a given origin can be written as theta equal to t squared plus t. So we have a circular motion. We have the radius of the circle, and we have the angle theta, the angle of rotation. With respect to time, it's equal to 2t squared plus t. Okay, at the first glance, we would think that we may use the normal and tangential coordinates because we have a circular motion. So let's see the questions in this exercise. A. Determine the angular velocity of m as a function of time. So we need to find omega. Omega is the angular velocity. From omega, we have to deduce its velocity v of t. So how do we find omega? Omega is in fact equal to d theta over dt. Okay, we know what is theta as a function of time, so it's very simple to find d theta over dt. So theta is equal to 2t squared plus t. The angular velocity, omega or theta dot, is equal to d theta over dt. It's equal to, so we have to derive this expression with respect to time. It's equal to 2 times 2t plus 1, and this will give us 4t plus 1. This is omega, the angular velocity. And we have to deduce v. V is in fact equal to omega cross r. Okay, omega that we found, it's equal, it can be written as omega in magnitude times the unit vector k. Why is it along k? So let's consider our circle. This is our circle of center O prime and of radius capital R. At t equals 0, the point that is moving on the circle was at O. So this is at t equals 0. As time passes, m will make a rotation. So m will move. At a certain instant of time, it will be in this point here. So let's draw ER and E theta. ER, let's draw it starting from M, this point M. So this is ER, and we have E theta. So this is our point M. We can also draw ER for sure starting from O prime. There is no problem. Okay, so what is the direction of rotation? The rotation is being in this direction, so the right hand rule will give us the direction of the angular velocity omega. Since our rotation is being in the counterclockwise direction, then k will be pointing towards you. It's perpendicular to ER and E theta, so we can write that omega is can be written as omega along k. Okay, if we go back to our velocity vector, v is equal to omega vector cross r. So omega is omega along k cross r. R is in fact here equal to the vector O prime m. So it's equal to the radius capital R times the unit vector ER. So this cross product will give us omega times r times sine of the angle between k and ER. So sine 90 is equal to 1. And we have to add a unit vector to our answer. K cross ER gives E theta. And yes, our answer is correct because V is along E theta. Okay, so the velocity vector is equal to omega r E theta. Omega is already found, it's equal to 4t plus 1. And finally, V can be written as 8t plus 2 along E theta or along tau, because E theta is the same as tau in the case of a circular motion. Question B, determine the angular acceleration of m. So we need to find now alpha. Alpha is equal to d omega over dt, or theta double dot. So let's derive theta dot as a function of time. The derivative of 4t plus 1 with respect to dt, with respect to time, will give us 4. So theta double dot, which is equal to alpha, it's equal to a constant, a positive constant. So our angular acceleration is a positive constant. This means that we have a uniformly accelerated circular motion, and this is the nature of the motion of m. So we have a uniformly accelerated circular motion. Question C, find the value of the tangential acceleration a tau of m. So we have to apply the rule AT or A tau is equal to alpha cross R. So alpha is equal to theta double dot. It's theta double dot along K, because omega and alpha have the same direction. Cross R, R can be written as capital R, the radius, along ER. So again, this is equal to R theta double dot times sine of the angle between K and ER, which is equal to 1. And we have to add a unit vector. So K cross ER is equal to E theta. And this will give us R theta double dot. It means we have 4 R along E theta. It's equal to 8 E theta. We can also find AT from the equation that states that AT is equal to dV over dt. So where V is the magnitude of the velocity vector. Okay, so dV over dt, we have, this is the magnitude of the velocity vector. The derivative of V with respect to time will give us 8. And the tangential acceleration is along E theta, so we can deduce it very quickly from the definition of AT, that is dV over dt. So we have two methods, okay? Finally, D, determine the acceleration vector A of m at time t equal 1 second. So the acceleration here can be written as an plus at, where at is already found, and we just need to find an. An is equal to v squared over r along the normal unit vector. V squared is equal to omega squared r squared. So an is equal to omega squared r along n. We have omega, where is omega? It's 4t plus 1. We have r, it's equal to 2 meters. And finally, we get that the normal acceleration is equal to 4t plus 1 squared times 2 along n. And we can get the total acceleration as 8 e theta plus 50 along n. So we just replaced t with 1 second. So this exercise was a practice about circular motion in normal and tangential coordinates, where we found the angular velocity and the angular acceleration.